Now the second session of this conference. Our first speaker will be the co-organizer of the conference, Professor Yurii Dumin of the Sternberg Astronomical Institute of Moscow State University. And the title of his talk will be Local Hubble Expansion, Current State of the Problem.
Thank you. My report will be devoted to the current state of the problem of the local Hubble expansion. And I am going to discuss both theoretical and observational aspects of this problem. In fact, the history of this problem is quite long. It began in 1932 and 33 from the works by British astronomer McVitie, who posed the question if the planetary orbits and other local dynamics can be affected by the expansion of the universe. And in the subsequent 85 years, a quite large number of other researchers dealt with this problem. Some of them are listed here, but of course, this list, I think, is not complete. The most frequent conclusion of these works was that the effect of the Hubble expansion at interplanetary scales should be extremely small or absent at all. However, I'd like to emphasize that the particular arguments used by the different authors often contradict each other very much. And besides, the most of these arguments are not applicable to the dark energy dominated cosmology. As one of the most striking examples of such a disagreement, I would like to mention the following. It is commonly believed, especially among the observational astronomers, that Hubble expansion should be broken by gravitational bending of the system, which is determined, for example, by the virial criteria. In other words, just the classical gravitational forces should break the global Hubble flow in the regions where mass is locally enhanced. On the other hand, the so-called Einstein-Strauss theorem, based on not on the classical gravity, but on the general relativity, tells us something which is directly opposite. Namely, if we consider an initially uniform distribution of the background matter and then cut some spherical volume and concentrate all the substance of this volume in a single point in its center, then, as follows from the solutions of the general relativity equations, the gravitational field inside this empty cavity will be static and given exactly by the Schwarzschild metric. And the cosmological Hubble expansion will be restored beyond this boundary of this cavity with the background matter distribution. In other words, according to this theorem, the Hubble expansion is suppressed not in the region of mass enhancement, but in fact in the empty volume. In fact, such result is not so much surprising because according to the standard formula of general relativity, Hubble constant is proportional to the square root of the matter density. So it's not surprising that Hubble constant formally disappears when matter density tends to 0. Therefore, as follows from the above example, any attempts to treat the problem of local Hubble expansion in terms of the classical gravitational forces in principle may be very misleading. Really, the global Hubble expansion exists even in the perfectly uniform universe, where there can be no any classical gravitational forces at all, because such forces can be produced only by inhomogeneous matter distribution. In other words, Hubble expansion corresponds to another degree of freedom of the relativistic gravitational field as compared to the degrees of freedom reduced to the classical gravitational forces. Indeed, the classical gravitational force has 3 components, and in general relativity, the gravitational field is described by the symmetric tensor, which has 10 components. So it is not surprising that there are additional degrees of freedom which are not reducible to the classical gravitational forces. Unfortunately, a lot of textbooks tried to estimate the local Hubble expansion just in the terms of classical gravity, or simply postulated the absence of Hubble, or simply postulated that Hubble expansion is absent in the small-scale systems. A typical example is the famous textbook Gravitation by Misnerton and Wheeler. I suppose that everyone knows this book. So in this book, as you remember, behavior of the small-scale systems, such as galaxies, in the expanding universe was pictorially described as a set of coins on the surface of an inflating ball. But in fact, no justification for such a picture was given. So, from my point of view, any treatments of the local Hubble expansion should be based only general relativity. Unfortunately, the above-mentioned Einstein-Strauss model is, of course, a very extremely oversimplified case because of the presence of the void. I should mention that a number of authors tried to consider some more generic situations, but unfortunately, a serious obstacle in this way was always the problem of separation between the peculiar and Hubble flows of matter in the spatially inhomogeneous system. Namely, if there is no ideal cavity or boundary with the background matter distribution is not perfectly sharp, then substance in the vicinity of the central mass will experience a quite complex radial motion depending on the initial conditions. And in general, we do not have any universal criterion to answer the question what part of this motion should be attributed to the Hubble flow and what part should be attributed to the peculiar motion. Fortunately, the situation is simplified very much. In the case of idealized dark energy degenerated universe, where the entire cosmological contribution to the energy momentum tensor comes from the lambda term or cosmological constant. Since the lambda term is distributed by definition perfectly uniform in space, it does not experience any back reaction from the additional point-like masses. As a result, it becomes not so difficult to consider the restricted cosmological two-body problem, that is motion of a test particle in the gravitational field of the central mass embedded into the cosmological background formed by the lambda term. I use the term restricted in the sense commonly used in celestial mechanics. It means that it implies that small mass moves in the field of large mass. So, in fact, mass of one of the bodies can be ignored. From my point of view, just the restricted cosmological two-body problem is the best way to get a simple but reliable estimate for the magnitude of local Hubble expansion, and such estimate can be used later as a benchmark in more sophisticated studies. I should mention that, in fact, the restricted two-body problem with lambda term was addressed in the last couple decades in a number of papers by different authors. But the starting point of all such considerations was Kotler's solution of the general relativity equations, written here. It is often called Schwarzschild-de Sitter solution, but I suppose that the term Kotler is better because Kotler obtained this solution much earlier. As a result of the above mentioned treatments based on this metric, it was found that the effect of the lambda term on the scales of planetary systems should be completely negligible. However, I would like to emphasize that the above metric suffers from the lack of the adequate cosmological asymptotics. Namely, it does not reproduce the standard Hubble flow at infinity. Therefore, the effects by the lambda term in this metric are not, strictly speaking, are not immediately related to the cosmological expansion. Maybe they probably describe only some part of the Hubble expansion, in fact. So, to formulate the restricted to body problem with correct cosmological asymptotics, it is necessary to perform transformation to the Robertson-Walker coordinates commonly used in cosmology. This was actually done in my paper published 9 years ago, and the resulting modified Kotler metric with cosmological asymptotics takes the form written here. As you can see, it is quite complex as compared to the original expressions. And it involves two crucial parameters. One of them is Schwarzschild mass, Schwarzschild radius proportional to the mass of the central body. And second is de Sitter radius, which is inversely proportional to the square root of the lambda term. If we are interested only in the first non-vanishing terms of the Schwarzschild and inverse de Sitter radius, which is actually a very good approximation, then these formulas can be rewritten in a more simplest form. So, if we have metric presented in the previous slide, then the equations of motion of a test particle can be obtained by a standard way as geodesics. The corresponding set of equations in general form is written here. As you can see, it involves three characteristic length scales. They are Schwarzschild radius, initial radius of the orbit, if we consider approximately circular motion, for example, and de Sitter radius. It is important to emphasize that for the realistic astrophysical systems, these three characteristic parameters differ from each other very much. For example, for the Earth-Moon system, they differ by 29 orders of magnitude. This makes the analysis of this system very hard. Unfortunately, by now, we did not succeed in the development of analytical perturbation theory for this set of equations. And even the numerical integration is quite difficult because of the above mentioned huge discrepancy in the characteristic scales. So, to simplify numerical integration, let us consider some toy model where difference between the characteristic scales, namely Schwarzschild, initial orbital, and de Sitter radii, is not so much as for real astrophysical systems. For example, let us take the initial radius of the orbit as the unit of length, and let Schwarzschild radius be 2 orders of magnitude less. And here you see the results of numerical integration of the corresponding equations for the different values of lambda term, or for different values of de Sitter radius. So you see that when lambda term is absent, and respectively de Sitter radius is infinite, we have a perfectly closed orbit. Next, when lambda term increases and respectively de Sitter radius decreases, these orbits become more and more spiral. The same results of numerical integration are presented for convenience in the next plot. Here you see the orbital radius as function of time. The curves with different colors corresponds to the different values of de Sitter radius. They are not monotonic but oscillating just because the initial orbit was taken to be slightly elliptic. And the dashed straight lines of the same color correspond here to the standard Hubble flow, that is to the case when there is no central massive body. As you can see from these plots, in some circumstances, the rate of the local Hubble expansion can be significant and in general approaches the rate of the standard Hubble flow at infinity. Of course, this is only a toy model, but I suppose that these results are very useful for future studies. So, what are the main conclusions from the theoretical analysis? A test particle orbiting about the central mass embedded into the cosmological background formed by the lambda term can really experience the local Hubble expansion. Therefore, our calculations argue against the commonly accepted intuitive point of view that the remote cosmological action would result just in a partial compensation of the gravitational attraction to the center. That is, that the orbit will be slightly disturbed by remain stationary. Unfortunately, as I already said before, it is difficult to get reliable numerical values for the realistic planetary systems because of the huge difference in the characteristic length scales. Besides, since the equations are strongly nonlinear, it is difficult even to predict how the other kinds of celestial perturbations, for example by the additional planets, will interfere with such secular Hubble-type effects. In fact, it is not clear in advance if the local Hubble expansion will follow the standard linear relation, because in principle, in the vicinity of the massive body, it could be strongly nonlinear. And of course, the value of the local Hubble constant in general may be different from the global one. So all these questions are still to be answered. Of course, the crucial factor supporting our interest to the cosmological effects at small scales are not the results of some theoretical calculations, but the fact that a number of observable phenomena, both in the solar system and local intergalactic volume, could be naturally explained just by the local Hubble expansion. As regards the phenomena in solar system, these are the so-called faint young sun problem, that is the insufficient luminosity of the young sun to support development of the geological and biological evolution on the Earth, the problem of liquid water on Mars, which actually has the same origin, the lunar tidal catastrophe, that is anomalous rate of recession of the moon from the Earth. Next, I should mention also the long-term dynamics of the fast satellites of a few planets, efficiency of formation of Neptune and comets from the planetary disk, and also some other problems which were mentioned in more detail in the paper cited here. But I would like to begin just from the lunar tidal catastrophe, because from my point of view, this is in some sense the most clean system where we do not need to take into account so many additional effects. And in fact, the main reason why we discuss the probable Hubble expansion in this system is the well-known fact that there is a considerable disagreement between the rates of recession of the moon from the Earth, which is derived on the one hand from the deceleration of the Earth's proper rotation, and on the other hand from the direct measurements by lunar laser ranging. Namely, the corresponding quantities differ by more than 2 times. Let me remind you briefly that in principle the effect of a recession of the moon from the Earth is known for a very long time. It is caused by the fact that the tidal bulge on the Earth's surface is not perfectly aligned in the direction to the moon, but slightly shifted in the direction of proper rotation of the Earth. This is just because the angular velocity of the Earth is greater than orbital velocity of the Moon. As a result of such shift, the motion of the Moon will be accelerated and proper rotation of the Earth decelerated. So it can be easily obtained from the law of conservation of angular momentum that the rate of recession of the Moon from the Earth is linearly related to the secular variation of the Earth's period of rotation, or in other words, the length of day. And I would like to emphasize that the above mentioned discrepancy, in principle it was discussed for a long time, but it became especially evident in the last 20 years when the accuracy of lunar laser ranging measurements became very high. Accuracy became very high and the errors were reduced very much. So to resolve this discrepancy, a number of suggestions were proposed. One of them, for example, is the correction of the Earth's deceleration rate by the data on the ancient solar eclipses, which enables one to cover the period, for example, about 3,000 years instead of 300 years. Unfortunately, the data on ancient eclipses are very contradictory, and the resulting values of Earth's deceleration can differ from each other by more than 2 times. Yet another proposal was to take into account a secular decrease in the Earth's moment of inertia due to the so-called glacial rebound. What is that? It is assumed that during the glacial period, a huge amount of ice in the polar regions compressed the Earth, thereby increasing its moment of inertia about the polar axis. Then, when the ice have melted, the Earth gradually restores its spherical shape, and this results in the decrease of the moment of inertia. So we should get some speed up of the proper rotation. And in fact, the first data on the secular variation of the moment of inertia of the Earth, which were derived in 1983, really gave some value which looked to be quite sufficient to avoid the discrepancy mentioned in the previous slide. Unfortunately, the subsequent analysis gave much less values of this quantity, about an order of magnitude less, and even some authors got the opposite sign. So from the modern point of view, the secular decrease in the moment of inertia seems to be absolutely insufficient to explain the lunar tidal catastrophe. Therefore, the problem of disagreement between lunar laser ranging and the data on deceleration remains as severe as before. I'm sorry, what's happened? Okay, thank you. So, in view of the above circumstances, it is interesting to consider the influence of the local Hubble expansion to resolve the above mentioned problem. Really, the immediate measurements of the lunar recession rate by laser ranging should involve, by definition, all possible effects. That is, both geophysical tides and the probable local Hubble expansion. While the indirect derivation of the same recession rate from the Earth's rotation deceleration, just by definition, involves only the geophysical tides. So the discrepancy between these two values, namely 2.2 centimeters per year, can be attributed just to the probable local Hubble expansion in the Earth-Moon system. And it can be easily calculated that the corresponding rate equals approximately 56 kilometers per second per megaparsec. Is this value reasonable from the viewpoint of large-scale cosmology? Let us assume that the local Hubble expansion is formed only by the uniformly distributed lambda term, or dark energy, while the irregularly distributed, that is aggregated forms of matter, begin to contribute only at larger scales. Then we can write these expressions, namely the local Hubble expansion, the local Hubble constant will be proportional to the square root of only the dark energy density, and the global Hubble constant will be proportional to the square root of the total density, where the second term refers mostly to the dark matter. So the ratio of the local to global Hubble expansion is given by this formula. In other words, if we take some typical values for the relative densities of the dark energy and dark matter, we can easily find that the global Hubble constant should be approximately 15% greater than the local one. In other words, it should be approximately 65 kilometers per second per megaparsec, and this is in fact in good agreement with the large-scale cosmological data, especially with data derived from supernova. So the above-mentioned fact, from my point of view, is a quite strong evidence in favor of the probable presence of Hubble expansion in the solar system. Another important argument is given by the faint young sun paradox. In fact, it will be discussed in more detail by Professor Föllner just after me, but let me briefly remind what is the problem. According to the models of solar evolution, its luminosity, L, should be about 30% less when the Earth was formed. This means that the mean surface temperature at early stage of the evolution of the Earth should be much less than now. In particular, all water would be frozen over 2 billion years ago. But on the other hand, there is clear geological evidence for the considerable volumes of liquid water on the Earth in the period about 3 or 4 billion years ago. And moreover, the lower temperature would be very unfavorable also for the emergence and development of the life on the Earth. In fact, the most of previous attempts to resolve the faint young sun problem were based on the assumption of the considerable greenhouse effect in the early atmosphere of the Earth. Such attempts were, the first such work were probably done by Sagan, and there were many subsequent publications. It was found that under the appropriate choice of chemical composition of the early atmosphere, it is really possible to obtain a reasonable range of temperatures for the entire evolution of the Earth. But unfortunately, the available information about the early Earth's atmosphere is contradictory and insufficiently supported by independent measurements. So I believe that this problem is still not resolved. Probably Professor Föllner will make later some corrections. So an absolutely new approach to avoid the above-mentioned discrepancy was proposed in the recent papers by Křížek and Sommer, who supposed that the increase in the solar luminosity with time could be compensated by the increase in the Earth's orbital radius, just due to the local Hubble expansion. In particular, these authors obtained that at such value of the local Hubble constant, the solar irradiation of the Earth should remain constant with very high accuracy, better than 1%, in the entire period of its biological evolution. However, as you can see, the value of the local Hubble constant, which they use, is substantially less than the value of the same quantity, which we discussed in the context of lunar tidal catastrophe. So the natural question arises, it is possible to reconcile these two values. With this aim in view, I have considered a set of various models of solar luminosity characterized by the parameter delta L, which is in fact the total variation in luminosity from the birth of the sun to the present time. And I considered a number of different hypothetical rates of the local Hubble expansion. These 4 plots correspond to 4 different values of delta L. And the curves with different colors correspond to the various rates of the local Hubble expansion. In the first plot, you can see that the green curve with designated 0.5 is just the case considered by Křížek and Sommer. You see that it really provides a very stable irradiation in the past. But if we take the larger values of the local Hubble expansion, for example 0.8, you see a considerable variation. However, if we consider another model with larger variation in luminosity, then, for example, the same value of the local Hubble expansion, 0.8, will give us more or less stable irradiation in the past. An important question arises if such model with delta L equal to 0.5 reasonable from the viewpoint of of models of solar evolution. As was explained to me by Professor Mede, such value of delta L in fact could place if we imagine the process like mixing in the solar interiors. This would imply that the sun had a small convective core. So I think that it's a very interesting option and it should be studied in future in more detail. As regards other systems where the local Hubble expansion may be important, there are a number of phenomena in the solar system which were already listed in Maya on the previous slide. I am not going to speak about them in more detail because they are much less studied than the faint young sun problem and lunar tidal catastrophe. Besides, I would like to mention that in the last couple decades, the high precision ephemerides of all solar system bodies, including the major asteroids, were constructed by a number of authors on the basis of optical and radio astrometry data. And these authors almost always claimed that a self-consistent picture of planetary motion can be obtained without taking into account any cosmological influences. However, I would like to draw your attention to the fact that such analysis involve a lot of fitting parameters. The number of such parameters may be something like 300. These are, for example, the unknown masses of asteroids, solar oblateness, effects of the solar wind on the radio wave propagation, and so on and so on. On the other hand, the local Hubble expansion was never included into the corresponding equations in explicit form. So the small resulting residuals might be merely a mathematical artifact, because it is well known from statistics that any empirical data can be fitted as accurately as possible, as accurately as desirable, if the number of free parameters becomes sufficiently large. I should mention also that if a local Hubble expansion is present in the solar system, it should be, of course, expected also in galaxies. But since the galaxy involution is very complicated by the formation of stars and their proper motion, this problem remains now, in fact, completely unexplored. At last, as was already mentioned in the previous report by Professor Karachintsev, the presence of Hubble expansion in the local intergalactic volume is a much more elaborated subject. I will not repeat the first three items because they were already discussed in sufficient detail in the report by Karachintsev. But I would like just to emphasize that in fact it remains unclear by now if the effective value of Hubble constant in the local group is smaller or larger than at the global scales. Besides, I would like to draw your attention to the fact that the most of theoretical works on the dynamics of galaxies in the local group employed the concept of anti-gravity force derived from the static Kotler metric. And unfortunately, as was already mentioned in one of the previous slides, such treatment has a limited scope of applicability because the original Kotler metric does not possess a correct cosmological asymptotics at infinity. And therefore, the corresponding force is unable to describe the entire Hubble flow in principle. Besides, we should have in mind that this effective force is adequate, strictly speaking, only for the restricting to body problem. That is when one mass is infinitely small. In general, there is no reason to assume the validity of this formula when both masses are comparable to each other, or especially to apply this formula to the many-body problem. In fact, there are many works which do so, but it is, I believe that this is just an assumption which is not supported by reliable theoretical calculations. So I think that, for example, the problem of missing dark matter in the local universe, for example, discussed in the works by Makarov and Karachintsev, could be caused just by the limited applicability of such formulas for anti-gravity forces. Of course, this is just a conjecture which need to be considered in more detail. And finally, as a concluding remark, I would like to emphasize that despite a lot of theoretical works rejecting the possibility of local Hubble expansion, I believe that this problem is still unresolved. Firstly, because the available arguments against the local Hubble expansion very often contradict each other. Secondly, because many of them become inapplicable to the dark energy dominated cosmology. And especially because a self-consistent treatment of the toy model, namely the two-body problem against the lambda background discussed in my previous slides, demonstrates the principal possibility of the secular cosmological influences at small scales. In other words, the Hubble expansion is not suppressed completely in the vicinity of a massive body. Besides, of course, I should mention that, again, that a few long-standing problems of planetology, geophysics, and celestial mechanics can be well resolved by the assumption of local Hubble expansion, whose rate is comparable to the rate at the global scale. And what is especially surprising is that many theories now believe that the possibility of local cosmological influences is strictly prohibited just by the available observational data, while a lot of observers believe that there are irrefutable theoretical proofs that Hubble expansion is absent at small scales. So from my point of view, the situation looks quite funny. And finally, I should say that there is still one important conceptual question to be answered. Namely, what is the spatial scale from which the cosmological expansion no longer takes place? This question is of crucial importance because otherwise the meter stick will also expand, and therefore it will be meaningless to speak about expansion at all. Just because in this case, if everything expands, we don't have a unit of measure. I cannot give a definitive numerical answer to this question, but I believe that the systems dominated by non-gravitational interactions should not experience the cosmological expansion. So the matter sticks, the solitude, and all such systems should not expand. That's all. Thank you for your attention.
We have about 9 minutes for questions.
So I still don't understand why people are even leading these discussions whether Hubble expansion exists around massive bodies. It should be possible simply to apply the Einstein's equations and find a solution, then people would see what they get. So.
Probably I didn't understand quite well your question, but I should mention, first of all, there was a number of works where people tried to solve equations, for example, for the fluid-like matter in the vicinity of the central body. But the main problem of such calculations is that it is usually, there is usually no reasonable criterion how to separate Hubble expansion from local attraction. There is no universal definition. As regards the two-body problem, as I told you, here can be solved in some reasonable approximation for the lambda-dominated cosmology when there is no back reaction. But when we consider more realistic cases, when there is also contribution from dark matter, for example, we again encounter the problem of, how to say, back action, because this additional matter, for example, dark matter, begins to fall into the central mass, and we don't know where is the Hubble expansion and where is the effect of local attraction. So this problem may be, besides of purely mathematical difficulties, there is some conceptual problem how to define accurately what is the Hubble expansion.
Yes. Can you argue why some systems not subjected to gravitational interaction would not suffer of Hubble expansion, and this like not expand?
Yeah.
And second point.
What is the first question?
The question is why you say you believe that some systems do not.
Why I believe? So let me answer. I believe so because Hubble expansion is essentially the gravitational phenomenon, and if the system under consideration is governed not by gravity but some other forces, in general, I suppose that there is no much reason to assume Hubble expansion, because if there is no gravity.
Well, but Hubble expansion is not, well, it is not strictly related, well, it is partly related to gravity, but it's not only gravity. You can imagine a system, you can imagine the Hubble expansion going independently from gravity. But the other point is, suppose you have an interferometer,
yeah.
Okay? And the Hubble constant corresponds, if I read correctly, about 2 × 10 to the minus 18 meters per second per meter.
How much it do?
2 10 to the minus 18 meters per second per meter. So
I can.
Okay. So in principle, one should be able to see an expansion also.
Yes, in principle. But sorry, if the interferometer itself also expands, how will you feel it? The problem that interferometer will also everything.
Okay, so then that means that then the expansion occurs also in local scale. Also the Earth is
if we would be able to make such measurements, of course this would imply that this is the fact, but by now we don't have such measurements, and of course my last item is just some speculation, which I believe reasonable, but I don't have any proofs.
I think your development of the Kotler metric is really a major step from the theoretical point of view. I have a minor question. You you have an equation relating the change of the Earth's rotation to the increase of the moon distance.
Yes.
It contains two terms.
This is well known.
Yes, yes. The point I wonder, is there no thermal dissipation to take into account into this interaction, because the tide are hitting the internal of the Earth, they produce waves at the surface, and are these thermal losses really negligible?
I'm not much specialist not good specialist in this subject, but I think the situation is follows. What is important in this consideration is how much is the shift, is the angle between the direction to the Earth and position of the tidal bulge, and this shift is caused in, how to say, it may be not so good to call this dissipation effects, but this is how to say, finite time relaxation effect. If I understand the situation correctly, the crucial issue here is not dissipation but finite time relaxation. And as regards the attempts to derive these quantities from the first principle, just from the parameters of the Earth, how much will be the deceleration. As I understand, the main problem in these works is that the people cannot reliably calculate this finite time how much is this finite time relaxation, which results in the shift of the bulge. If I understand the situation correctly, this is the main problem.
But you are using observed. Everything you're doing is observational.
Yes.
Then there is no need for theory. If the observation okay. And if you look at angular momentum conservation, it's true that the dissipation will determine what will be the angular momentum change. But if you are looking at observed angular momentum change, you don't need a theory. It's a reply to...
yes, yes. But I would like to make the following remark. In fact, the value of circular increase in the period of rotation of the Earth is a poorly known quantity because the rate of rotation of the Earth experiences quite complex variations in time. And the value which I used was derived from the astrometric observations for the period somewhat greater than 300 years, when we had sufficiently reliable astrometric data, and all my discussion referred just to this case. In principle, the Earth's rotation may experience also some kinds of quasi-periodic variations on the time scales about 100 years or even greater, and such variations can change the average linear trend. And then the corresponding predictions for the recession rate will be very different. There was a large discussion in the literature about that subject, particularly the attempts to make correction for ancient eclipses and so on. But, for example, in my first work, I used some values of the deceleration corrected for some eclipses, and I got in that work the value of Hubble constant not 56 but 33. And from theoretical point of view, I'm not sure what value of the deceleration is correct, but I think that if we take just the value for 300 years without any further corrections for ancient eclipses, for circular decrease in the moment of inertia, then just this value of deceleration without any further correction gave the value of local Hubble constant well in agreement with large-scale cosmological data. From my point of view.
Thank you, speaker again, please.
Thank you.